Hi all. Today we are into module 5 of structure analysis 1. As you can see over here, module 5 includes arches, theory of arches and Etty's theorem, then analysis of three-hinged arches, support reaction, normal thrust and radial shear at any section of a parabolic arch due to simple cases of loading. So these are the portions which we need to cover as the first part of module 5. So we'll see arches in detail. So arches are structures composed of curvilinear members resting on supports, and they are used for airplane hangars and long span structures. They are curved beams made of stones or bricks supporting each other and supported at ends by means of abutment. Now you have various types of arches based on geometry, and now that you have a figure over here which includes what are the main parts of a arch. So as you can see, that curved shape is there, which is what we call as an arch. So this is that curved shape. Then you have the center point, that is these arch will be a portion of a parabola or a circle. So that is the center point which is of the circle or the arch. Then you have the rise, which is the centermost topmost point, and you have the crown over there, that is known as the crown. Then you have this portion that is known as a haunch, then the other portion that is known as the haunch on both sides. Then you have like this portions which are known as vouziers, that is you keep the bricks or stones in this manner, it is known as vouziers. Then you have the outer arch portion known as extrators, inner arch portion known as intrators. Then you have springing and abutment. See, abutment is the support, this portion is known as the abutment, and springing is the region between the abutment and the starting of the arch. Anyway, it is also the beginning of an arch, that is known as springing. Then you have the abutment, which is the support. Then you have the span, which is marked as the center line, from center line of the arch. Then you have the span, that is inner span. So the topmost portion, crown. Then this region, this stone is known as the keystone. So these are the main parts of an arch which you need to study for the theory portion question. So next we have a small comparison between beam and arch. So we have a beam and arch comparison. That is, the main reason why you go for a arch or you prefer an arch is because the bending moment is less in an arch while compared to a beam. So what happens is, for longer spans you prefer arch than beam. So this is a figure which shows a beam which is supported at 2 points, simply supported A and B. Then you have a load, concentrated load P, which is acting at a distance L by 4 from A. Now while you calculate with the taking moment about any support equal to 0, you get the support reactions as 3P by 4 and P by 4. Now what you do is you just take a distance x from A and you just calculate the bending moment. Then you will see that the bending moment is 3P by 4 into L by 4, that is equal to 3PL by 16. In the same way, now you go for an arch which is supported at two ends, that is A and B. Then you have a load which is at a distance of L by 4 and the vertical distance is Y. Same way, using the sigma m at any support equal to 0, you can determine the support reactions. One you will get it as 3P by 4, the other one you get it as P by 4. Now what you need to do is you need to calculate this H, because you have H, that's a horizontal thrust in the case of arches, which is acting inwards at both supports. So what you do, at a distance x from A, you just calculate the bending moment. You get it that 3P by 4 into L by 4 minus H into Y. So what happens is, you can see that you have a reduction factor. Here you have the bending moment as 3PL by 16 and you have a reduction factor HY. So this is what makes the arch more attractive than beams. Now you just need to compare what cable and arch difference is, because we have seen cables in the last module. So cable takes the shape of loading, that is whatever be the loading, cable takes the shape, and bending moment is 0 at every section in the cable, and it takes up only tension. This is the figure of a cable, as you know we have studied, and you have the outward edge in the case of cable. Now for arches, they take up compression, whereas cable takes up tension, and the vertical reactions are inward, as we have seen horizontal reaction. Now we have yet another figure, that is in both these figures you have arch only, but structurally the first one is an arch and the second one is a beam. The reason is because the first one has a horizontal thrust. Whenever this horizontal thrust is also induced at the supports, then only you call it as arch action structurally. If horizontal thrust is not induced at the supports, you call it as a beam, not as an arch. Now you have the types of arches as 3-hinge, 2-hinge and fixed arch, and you know it's statically determinate, indeterminate. Now how you tell it is statically determinate and indeterminate? Sigma h equal to 0, sigma v equal to 0, sigma m equal to 0, that's the equilibrium conditions generally you have. And whatever a number of unknowns you have, number of unknowns minus equilibrium condition gives equal to 0, you call it as statically determinate. And the other cases you call it as statically indeterminate. Now here you can see that you have 3-hinge, it's a 3-hinged arch. 1, 2, 1, 2 and another one. So what happens is these are the hinges at the support. You have 2 support reaction, number of unknowns is 4. And whenever a internal hinge occurs, it gives you an extra equation. So your normal equation is 3 and plus 1 you have 4. So 4 minus 4 equal to 0. The other case you have 4 unknowns and 3 equation, 4 minus 3 1. Here you have 6 unknowns and 3 equations, 6 minus 3 3, statically indeterminate. And here it is given that 2 hinge at support and 1 at the ground. Now this is the small difference, certain differences between 2-hinged and 3-hinged arch. Then one is static indeterminacy is 1, the other static indeterminacy equal to 0. Then the other one developed temperature stress, then the central rise increases, so no stresses. Because in this it developed temperature stresses because expansion is not permitted. Here expansion is permitted, the central region can rise. This is structurally more efficient, easy to analyze, additional expenditure for the central hinge. The stresses due to sinking of support, no stresses due to sinking, it's determinate. Now yet another classification of the 3-hinged arch, you have parabolic and circular or segmental. Parabolic, you have 2 types, support at same level and support at different levels. Circular or segmental arch, it's a part of a circle. Now you come into parabolic arch. So for parabolic arch, the one important thing which you need to notice, now we are seeing the case where the supports of a parabolic arch is at the same level. So you can just draw the figure, that is, this is very important, supports are at the same level, because when supports are at different levels you have different equations and different method of doing the problem. So see, you have an arch AB and here it is given in the figure that both are hinged. This is a 3-hinged arch, okay. So C you have a hinge, then A you have a hinge, then B you have a hinge. So this is a 3-hinged arch. The span of the arch is L, and you have L by 2, which is center. You have rise H, it's given. You are taking a point D, which is vertical intercept is Y, horizontal intercept is X, okay. What do you mean by vertical intercept is vertical height is Y, that is the D is a point which have the vertical height as Y and horizontal distance as X, clear? Now I have told you that this is a parabolic arch and this is a 3-hinged parabolic arch. So from the name itself you will understand that for a parabolic arch it's a parabola. The arch is parabolic in shape. So what's the equation for a parabola? y is 4hx by L square into L minus x. What is y? That is this vertical intercept. At any point, at whichever point you need to know this vertical height y, you should use this equation. And it is 4hx by L square into L minus x, where L is the span of the arch, h is the rise, L is the span, then x is this horizontal distance. Clear? Now you have next equation, that is tan theta, because we need to calculate tan theta in certain cases. So tan theta is dy by dx. That is, you have your y equation as 4hx by L square into L minus x. That y divided by dx will give you tan theta. And you can calculate theta. Okay. Now another important thing for an arch is, you consider any point on an arch, as in this figure. You have vertical shear and horizontal shear. At any point in an arch, you have vertical shear and horizontal shear. Why? Because this arch, I have told you in the beginning that it has a horizontal inward reaction. So at any point, you have horizontal shear and vertical shear. So vertical shear is the algebraic sum of the vertical forces, and horizontal shear is the algebraic sum of the horizontal forces. So at any section if you consider, you have vertical shear and horizontal shear. What do you mean by vertical shear is the algebraic sum of the vertical forces that is considered up to the section. In the same way for horizontal shear, as this is present in the case of a arch, you have normal thrust and radial shear. So normal thrust at any section of an arch. Normal thrust is notated by N and radial shear is notated by T. And the normal thrust makes an angle theta with the horizontal shear. Now what you need, by writing down the resolving normal thrust and writing down sigma h and v, you can see that normal thrust is given by v sin theta plus h cos theta, and radial shear is given by v cos theta minus h sin theta. You should by heart these equations. Okay, so it is from this only we have written n, and you have the theta and correspondingly both. One is v sin theta and h cos theta. It's a horizontal and vertical component. In the same way, radial shear q is given by v cos theta minus h sin theta. Now these are the equations that are required for doing the problem of 3-hinged arch, parabolic arch, for which support are at the same level. Now just note down the problem. That is, a 3-hinge parabolic arch hinged at the support and at the ground has a span of 24 meter and a central rise of 4 meter. It carries a concentrated load of 50 kilonewton at 18 meter from the left support and a UDL of 30 kilonewton per meter over the left half. Determine the support reactions N and radial shear at 6 meter from the left support, and also find the moment at 6 meter from the left support. So first what you need to do is read this question and draw the figure. Sometimes figure may not be given in the question paper. So accordingly you should know to draw the figure after reading the question.